Hello, grade 12 learners. I would like to talk to you about the Maxwell-Boltzmann distribution curve. What is the Maxwell-Boltzmann distribution curve? In simple terms, the Maxwell-Boltzmann distribution curve is a curve which shows how available energy is distributed amongst the particles in the system. On the board, we have this diagram. This representation over here is the Maxwell distribution curve. So let's label this curve, curve A, and let it be the initial curve that we have. Okay, what happens over here? As you can see, there is a vertical line which separates two regions of the curve. There's that region over there and the region over here. In each of the regions, there are particles. The particles in this region do not have enough kinetic energy to can give effective collisions. Whereas particles in that region have got enough kinetic energy to can give effective collisions. Now, as you can see, we have the vertical line over there. The vertical line represents the activation energy. The activation energy. Suppose you still remember what is meant by activation energy. The minimum amount of energy which is required to start a chemical reaction. Now, there are three factors that can actually cause a change in the formation of the curve. The first one is temperature. The second one is a catalyst. The third one is concentration. Let's start with temperature. Suppose the temperature of the system increases. The temperature of the system changes. In this case, that change is an increase in temperature. So what is going to happen is that, as you can see, the curve has got steepness at different points, right? So if temperature increases, you're going to find that the steepness of the curve decreases at different points. So you're going to have something which will look like this. Now, what happens is that the number of particles in this region decreases, whereas the number of particles in that region increases. You will now have more particles which will have enough kinetic energy to can result in effective collisions. The number of particles which do not have enough kinetic energy to can give effective collisions decreases, whereas the number in that region increases. Let's label this curve B. Let me just indicate that this curve has got to do with the change in temperature. Okay, one other thing which you have to take note of in this situation is that there is no change as far as the activation energy is concerned. So meaning that if you manipulate temperature, in other words, if you change temperature, that change which happens as far as temperature is concerned does not affect the activation energy. Now let's move on to the second factor, the addition of a catalyst to the system. If a catalyst is added to the system, nothing will happen to the steepness of the curve at different points, meaning that the curve will remain as it is. The initial curve will remain as it is. The only thing which is going to change is the activation energy. We're going to get a new activation energy. So, meaning that we're going to get something like this. Let me use the blue marker. So, the activation energy will shift to the left. Just say A new. So this will be the new activation energy. Now, the shift in the activation energy to the left makes room for more particles to have enough kinetic energy so as to lead to effective collisions. So this is basically what happened. I mean what happens as far as the addition of a catalyst is concerned. So let's label, okay, this one, let's just put the letter C over there, just to indicate that we have got something different. The last factor that you have to look at is that of concentration. What is going to happen if the concentration of the substances over here increases? Concentration actually has got to do with the number of particles in a given space, or the number of moles in a unit of volume. So, if concentration increases over here, this is what is going to happen. This is what is going to happen. So obviously, the number of particles will increase. As the number of particles increases, you're going to find that some of the particles possess enough kinetic energy to can lead to effective collisions, whereas other particles will not have enough kinetic energy to can lead to effective collisions. This is basically what happens. Okay, let us go back to the original, the initial curve A. You find that you've got this region that has got particles that do not have enough kinetic energy to can result in effective collisions. And in that region, you've got particles that have got enough energy, enough kinetic energy to can lead to effective collisions. Okay, so increasing temperature decreases the number of particles in this region, and it increases the number of particles in that region. We'll have more particles with enough kinetic energy to can give us effective collisions. Okay, if you add a catalyst to a system, nothing is going to change as far as the shape of the curve is concerned. Only the activation energy will shift to the left. As it shifts to the left, it will make room for more particles to move to that region. The region with particles that have got enough kinetic energy to can lead to effective collisions. And in the case of increasing concentration, you are going to have more particles. And some of those particles will have enough kinetic energy to can result in effective collisions, whereas some of the particles will not have enough kinetic energy to can give us effective collisions. In short, this is basically how we make use of the Boltzmann distribution curves to sort of like see how particles are affected when energy changes in terms of the three factors which I've put above when they are manipulated. Thank you very much.